Exercise 17D, graphs of derivative functions. Once we have found the derivative, be it the formula as to what we'll be able to find the instantaneous rate of change at any point on a graph, we can now then turn that formula into a graph itself. The skill that we need to be able to learn is that if you can identify or read a derivative graph, can you find the original from which that was made? Let's just have a look at some of these. So for a start, as a reminder, if a graph has got an incredibly positive gradient, it's referred to as strictly increasing. And you'll see this terminology here, strictly increasing. And you'll see here we've got this rather horrible, complicated definition being the interval where x2 is greater than x1 implies f of x2 is greater than f of x1. What on earth does that mean? That means as x increases, the y increases. That's what that means. So strictly decreasing would be the opposite, where the interval where x is 2 is greater than x is 1 implies that f of x2 is less than f of x1. Obviously, the only thing that stays the same is that we must always refer to looking at the rate of change as x increases. We always read from left to right. We don't go the other way around. The word strict comes from the fact that there's strict inequality signs. That means just the greater than or less than symbol instead of greater than and equal to symbols. Example 1, match the graphs to the appropriate derivative graph. So, one strategy is to make an estimate as to what the equation might be for the original graph that we can then use that to estimate which one of the following that graph is. So let's have a look at A at the very top there. This one here. That looks like a quadratic to me, and it looks something that would be very much a y equals x squared type graph. Well, if it's a y equals x squared, that means the derivative would be 2x or some version therein. So all I need to do is to look at which of the graphs on the right would be the equivalent of y equals 2x. Well, it wouldn't be capital A because it's going the wrong direction. It's a negative gradient. It could be B. It wouldn't be C because C, the capital C there is a quadratic and it's not a linear graph. It's not D because that's not linear. E is linear, but it's flat. So that would be the equivalent of saying if y equaled 2. And then F is also flat, but this is a 0. So the only one it can be is B. Another way you can look at it is having a look at what's happening to each of the graphs. Let's have a look at these two graphs here. This graph on the left, the one that's been circled with a little a, it's decreasing until it reaches a turning point, which would be 0. So I'll highlight that in a dark blue. So that point is when it would reach 0. The graph is then increasing, and it's a positive gradient. If we look at the graph that we've matched, up until 0, the graph is below the x-axis. That is because any part that is below the x-axis represents a negative gradient in the original. So we've got a negative gradient up until x equals 0, and so therefore the derivative graph is below the x-axis until 0. We have a turning point at x equals 0 and an x-intercept in the derivative graph at x equals 0. Therefore, an x-intercept in the derivative graph then represents either a turning point, a point of inflection, or the category that we call those stationary points, or points of 0 gradient. When the derivative graph is above the x-axis, represents a positive gradient in the original graph. And we can see there on our two that we've matched. This understanding of this knowledge can help us when we have no idea what the equation of the original really is. So let's look at the other graphs. It might be useful to be able to separate these by looking at some of the graphs that have turning points. So if we look at B, there's a turning point here and a turning point here. So we need to find which of the derivative graphs have two x-intercepts at approximately those points. So one should be around about x equals 0, one might be, I don't know, x equals 4 or something along those lines in the positive. So graph A only has one x-intercept, so it only would refer to an original graph with only one turning point. But graph capital C is exactly what we're looking for. It has two x-intercepts to represent the two turning points. And let's double check. There's a positive gradient here and a positive gradient there. The derivative graph is above the x-axis here and above the x-axis there. And then it's got a negative gradient here and it's underneath the x-axis here. So those two certainly match up. Let's have a look at C. Now this one has a constant negative gradient. So it's just sloping down. It has a few points of inflection. There we go. So we're looking for one that has 2 points of two x-intercepts in the derivative graph, but also we can find anything that has a derivative graph which is all underneath the x-axis. And every single one of these has a derivative graph that's got some part, at least some part, either on 0 or above 0. The only graph that this could possibly match would be this one here, with its two turning points, one there and one there. So therefore, those two would be a match. Let's have a look at D. D is a negative, negative parabola. So it would probably be something like y equals negative x minus 1 squared. So therefore the derivative would be approximately something along the lines of negative 2x. So it should be a negative linear graph. And the negative linear graph here, and in fact, it'll probably be approximately that. So therefore, the only one that matches that idea is this one at the top here. So let's just double check. It should have one turning point just after the y-axis here. There it is. So that represents that turning point. It should have a positive gradient up until then, and then negative gradient and negative gradient. So those are a match. E, this one is a horizontal line. It is flat at about -4. So if it's flat all the entire time, that means that it has 0 gradient for every part of x. So out of these two, the only ones of these that suggest that it's flat for all parts of x is going to be F, because this is suggesting that for all x in the original, the derivative is 0, which leaves F with E. F is a linear graph, so it has a constant gradient. It has the same gradient for all values of x. It's positive, so we can see it's positively going up, therefore it matches to this one here. So, example 2, the path of a particle is defined by the following equation. So it's a restricted graph. We're only drawing from 0 to 4, and it is a cubic. So we're going to sketch the graph of the function above. So the first thing you might want to do is find out when x equals 0. So that's going to be y would be equal to 0 plus 2, 0 minus 2, and 0 minus 3, which would get me positive 12. And then we also want the end point when it's equal to 4. So 4 plus 2 is 6, times by 2 is 12, times by 1 is also 12. It's got 3 x-intercepts. One's at -2, one at 2, and one at 3. But since we only care for this interval, the only 2 of these that I care about will be 2 and 3. It is a cubic, which means it would actually normally start from down here and then move my way around. But we don't have to draw from there. Should look something like this. I won't worry about turning points for this one just yet, although we can find out what those are, but we'll talk more about that in chapter 18. Find the direction of motion when then the x value is equal to 1. So we can see when x is equal to 1 here, it's going downwards, so it'll be negative. But if we need to find a number, what we'll need to do is we'll need to expand this cubic. We can actually use our concept of derivatives to find the actual number for when x equals 1, what the actual rate of change is. Here it just says find the direction of motion. We can just say negative at this point because it's sloping downwards. But if we want to give more detail, it says here the path of a particle defined by the following equation. So I'm going to assume this is meters over time here in some sort of seconds. So the direction of motion is negative and it's moving at -7 meters per second. So when the direction of motion when x equals 3, well, this one, it's being positive. It's spinning, it's moving up. It's not flat. Don't get confused at the fact that it's an x-intercept and say that it's 0. No, it is positive. And again, if we want, we can actually find the very specific value by using the derivative. And that's 5 meters per second. Using your CAS calculator, find a point to 2 decimal places on the particle's path where the path is inclined at 60 degrees to the positive direction of the x-axis. So what does that mean in plain English? Well, what that means is that if I was to draw my axes, this is the positive direction of the x-axis, and I have this graph here. If I was to do a line here, the angle of the tangent line, if I was to draw on, would be 60 degrees. So that's what it's suggesting here. So we need to actually combine this with the previous topic, which is, of course, trigonometry. As you might be aware, tan of an angle is opposite over adjacent, which is the same as saying rise over run. So if you do tan of the angle, you will find the gradient. So tan of 60 degrees, if you remember your exact values triangle, there's 60 degrees, there's 30, 1 root 3, 2. So it'll be root 3 over 1, which is root 3. And then we need to go and solve accordingly to 2 decimal places. We need to solve for the value of x. I think you find a point. So we'll need to find out when the gradient is equal to root 3. So we're going to solve. So I've entered into the CAS calculator and I've got my 2 answers to decimal places. So which value of x do I choose? Well, remember that the domain is from 0 to 4. So we can't have any negative x values. So we'll use that positive one. So x is equal to 2.7, we'll say 71. And then all I need to do is copy that across. And what I'll do is I'll define the original function. And then I can just put in this value here and I get my y value. The last question says, are there any points on the path which satisfy the situation described in D? Well, technically speaking, yes, but it's not within the domain. So I can say know as x is equal to negative 0.706 is not in the domain.